One thing that I didn't mention yesterday, but it bears mentioning, is I told you for any triangle, you can have, it doesn't matter, I'll use PQR today. This is P, this is Q, this is R, so this is little p, this is little q, this is little r. I said that for a triangle that looks like that or that has those vertices, p over sine p equals q over sine q, which is equal to r over sine r. And we looked at a number of examples. And again, they're not too difficult. You have to get to know your calculator and how it works and how you have to enter things. But that's for any triangle. You can use that for a right angle triangle. This is like a really important multi-purpose tool, because if you have a right angle triangle and you forget SOHCAHTOA, you can use this and it will work. It doesn't matter that one of the angles is 90. What matters is if one of the angles is not 90, you have to use this. Okay. Anyway, I'm just going to open it up. That's sine law, the sine law. I'm going to open it up for questions. Does anybody have any questions you would like me to go over from 1 through 5? Well, that's good on a lot of levels because it tells me that you understand the sine law, which is a major part of this unit. And it's also good because then we have lots of time for today's lesson, because today's lesson is, I mentioned this yesterday, it's a pretty greasy kind of thing to wrap your mind around. It just slips out of your grasp every time you think you have it. It's pretty messy. So this is the very next lesson in your unit. It's the second part of the sine law in your textbook, so it's still section 2.3 in your textbook, but it's part 2, and it deals with what's called the ambiguous case of the sine law. And this is the kind of topic that I enjoy teaching it, but it's very difficult to teach because it's a challenging concept. And it's also the kind of topic that although you need to know this material for the exam in this unit, the likelihood that it would be on the final exam is pretty slim, and you don't need to know this to move on to 30 or to calculus. In fact, if you ask somebody who is taking calculus in university, can you explain the ambiguous case of the sine law? They're likely to answer, well, I remember being taught it. And I remember understanding it at the time, but no, I can't help you. I don't remember it. So if you find yourself in that position, it's normal. It's natural. So we have to be able to identify in this lesson when a triangle is ambiguous. We will talk about what that word ambiguous means in a minute. If it is an ambiguous triangle, then we're going to have to find out how many different solutions there are. And it turns out that a triangle, if it's ambiguous, can have a different number of solutions. Well, I'll tell you right now, the ambiguous case of the triangle might have no solutions. The triangle, in other words, might be impossible to construct. The ambiguous case of the triangle might lead to only one solution, which means given the information of the triangle, there's only one way you can draw the triangle. Or if I give you the information in a triangle that's ambiguous, it's possible that you can get two answers. So it's possible for Ali to work on it and for Joel to work on it and get two totally different answers that are both right. And that really has to do with the word ambiguous. And in the end, if it is ambiguous, you have to be able to solve the triangle. So for all of the triangles in the warm-up, we're going to be given, and this is very important, we're going to be given two sides and an angle that's not between the two sides. And this is going to be the test for ambiguity. Anytime you have, ambiguity is another way of saying it's ambiguous, which I will explain in a minute. Anytime you have two sides and an angle that's not between the two sides, the triangle is ambiguous. And you're probably getting tired of hearing the word ambiguous without knowing what it means, but that's the case. And when we draw these, I would like you to get into the habit of drawing the angle that you know in the bottom left-hand corner of your diagram, just like I've got it here, and having one side connected to that angle and the other side across from the angle. So in the ambiguous case, you're always going to know an angle and the side across from it, but I would like you to draw it this way. When this happens, we have to consider the ambiguous case of the sine law. Okay? So that's just an identification of when it happens. That's not an explanation of what we're even talking about. What does ambiguous mean? Well, open to more than one interpretation, having a double meaning. It doesn't mean that there's not a right answer. It means that if you interpret it one way and you interpret it a different way, they're both correct interpretations. And both answers are correct. So that's what ambiguous means. In other words, if we have a triangle like this, maybe the triangle can be drawn in two different ways correctly. And to introduce us to this idea, to warm us up to this idea, let's look at warm-up number 1. It says in triangle ABC, angle A is 30 degrees, side A is 24, and side B is 42. Now, I don't know if you remember, and I'm going to actually, let me give you guys rulers. I would like your diagrams here to be reasonably well drawn. So if you have a ruler, get a ruler out. I'll walk around with some rulers and give them to you. I don't know if you remember, but earlier I said I want you drawing them a certain way so that the angle that you know is in the bottom left-hand corner. So that's our starting point, is to consider a horizontal line, and this is not a side of a triangle yet, and draw an angle that is the 30-degree angle. It doesn't have to be measured. If you do have a protractor, then that's fine, but it doesn't have to be measured. You with us, Jack? Now, if you take a look at what's going on here in the information in the question, it says that side A is 24 and side A is across from angle A. So the next thing is to make sure we understand that's angle A. And we're always going to draw it this way. And all of the questions in your textbook, at least initially, and all of our examples will be A, B, C, and it will fit perfectly. And then you get one where they give you angle B instead of angle A. Well, just put angle B at the bottom. We always want the known angle for the ambiguous case of a triangle to be in the bottom left corner. Now, side A is 24, and that has to be across from angle A, but you're not going to draw it just yet, okay? Well, I guess you can draw it if you like. You can draw that. I take it back, draw it. So you're going to reproduce this as closely as you can on paper and draw that line, which is 24 long, from the end of the red line down to the horizontal. Now, the other side is 42, and that's side B. That's this side. So, again, what I want you to get in the habit of drawing all the time is something that looks like this, where you know this angle, this side, and this side. Okay? Those are the numbers you're given. Now the question is, how many different triangles are possible? Well, so would you agree that this is a triangle that's possible? The triangle formed by the red, the black, and the bluish lines is a triangle that's possible with those conditions. I would like you to rack your brain, think of it as a puzzle. Can I draw another triangle? Can I make the bottom side, which is C, can I make it a different length but keep everything else the same? All of the numbers the same. How would I do that? Like, I don't want an answer just yet. I want you to think about it. How can I draw? I have to keep the 30 degrees where it is. I can't change that. I can't change the length of B. And I can't change the length of A, but can I change how I draw A? So hand up and then down if you think you know that you could draw A in a different way to get a totally different looking triangle. It would still have 30 degrees, still have 42, and still have 24. This is what you would do. You'd take this line of 24, let's draw it to there. These two triangles, I guess I should put in, it doesn't matter. I'll go with that bluish color again. I think it was this one. These two triangles, this triangle here, and this triangle here, both have angle A as being 30 degrees. I'll toggle back and forth between them. Both have angle A as being 30 degrees. Both have side A as being 24. Both have side B as being 42, but they're different triangles. So the answer to this question is there's two triangles, but we're not quite done because there's a lot more going on here. But we're going to write an answer here and say two triangles. Now you're asked to sketch the possibilities. So one of them would look like this, where we started. This is the most reasonable thing. This is what people think it's going to look like. It's got to look like that, right? And maybe I'll give you a heads up here. If you have an ambiguous triangle, this is an ambiguous triangle because you could solve it this way and somebody else could solve it this way and you're both right. And you find angle B using the sine law, this is really important for later, your calculator is going to tell you this angle. It's not going to tell you that angle. It will always tell you the smaller of the two angles. Now, I have a different question for you. So you've got them both drawn. You've got the answer to the question that there are two triangles. I have a question for you. Is it possible that I gave you angle A, side B, and I give you a different length for side A so that there's no triangles? Could I get no triangles if I changed the length of side A? Can you give me a number that I could change the length of side A to so that I would get 0 triangles? Jack? Side A must have a length. So I'll repeat my question. That's my fault. Can you give me a non-zero length of side A that would still give no triangles? Will? 1. I mean, imagine it's 1. Think of this side A as being, I always call it the dangling side. If it's only 1 long, if side A was 1, you're not going to be able to form a triangle, are you? It doesn't matter how long or short side C is. And at this point in time, I'm just getting you to think about things. So it's possible, if it's ambiguous, that there's no triangles. It's possible that there are 2, like there is in this first question. I want you to really rack your brain here, and I'm trying to attack this topic from many fronts in the hope that it sticks. Is it possible that you could come up with a length of side A that would give only 1 triangle? And if you think it's possible, can you give me the number? Or a number, because there's 2 different possibilities here. Sasha, do you have an idea? 21? Perfect. What kind of triangle would we create if we made length A 21? It would be a 90-degree triangle. And you've remembered something that you asked about and we were talking about way at the beginning of this unit, where I said sooner or later you're going to know that the sine of 30 degrees is 1/2. That when you have a 30-degree angle, the height of that triangle is going to be half of the hypotenuse if it's a right triangle. So imagine, well, let's move ahead. We'll come back to that. If, in other words, if the length of A is exactly equal to this distance, then guess what? That thing dangles down, dangles down, dangles down, and it will only form a side in the triangle when it's vertical. Is that what you had in mind, Jack? Or do you have something else? Yeah. So let's take a look at number 2 now. Number 2 says, oh, look at that, 21. If we change this entire setup so that side A is 21, take a minute and draw that. And maybe you don't want to draw the dangling side just yet. But you want to draw the basic setup so we have 30 degrees and then we have side B is 42. And the swinging side, the dangling side is side A, which is 21. The height of this line, that blue dotted line, the reason why in question 1 we had 2 triangles was because A was bigger than that line. So if I go back to this situation here, I better reset this. If I go back to this situation here and I look at that vertical height, the reason why we got a triangle here and a triangle here was in part due to the fact that side A is bigger than the height. Okay? In part. There's another reason we got 2 triangles that has something to do with side B. So in question 2, it turns out, and if you look up here, I've set it up so that it looks nice. If I rotate this, and you might want to look at the other screen, it comes down, 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 and it only connects when it's hanging straight down. In other words, the length of side A is exactly equal to the height of the triangle. Well, what is the height of this triangle? If I said to you, find h in this triangle, then you could use the Pythagorean theorem. You could look at this triangle, and you could say in that triangle, sine of 30 degrees is the height of the triangle, which is opposite. So h here stands for the height, which is opposite to the 30. It doesn't stand for hypotenuse. Over the hypotenuse, which is 42. And can everybody cross multiply to solve that for h? So you're going to take 42 sine 30. Should get 21. Well, that's the point of question 2, that if this height is 21 and the dangling side is 21, the dangling side doesn't make contact with that horizontal line unless it's hanging straight down vertically. If it's even off a degree in either direction, there's going to be some air at the bottom and we don't form a triangle. And that means that there is only one triangle. It's this triangle. So in this particular case, you have one triangle, and that's the answer. One right triangle. In the previous question, I didn't put it, but there were two triangles, and we would call those two triangles two oblique triangles because they're not right triangles. Any questions with 2? I hope it's pretty clear how many triangles we're going to get here. This isn't quite to the extreme that Will suggested by picking 1 for side A, but 16 is too short to even connect to that bottom piece. So the bottom piece won't exist. The key is that this is less than the height. We've already calculated the height, but I'm just going to put of 21 centimeters. So if it's less than the height, then you're not going to form a triangle. 0 triangles. I hope it's clear why I've chosen 30 degrees here. Because when we find the height using sine equals opposite over hypotenuse, we get 21. We don't get some kind of weird set of decimals. And now, so any questions with 3? Now I'm going to ask a difficult question. And it's the one that some people won't even consider. It's possible to get one triangle, only one, by changing the length of side A, but that one triangle would not contain a right angle. How could you possibly have a different length for A? We've said if A is less than the height, then you get no triangles. We've said if A is equal to the height, you get 2 triangles. I've said that if A is more than the height, the words I used were in part because A is more than the height. In part, we get 2 triangles. But there's something else. If we go back to number 1 and these 2 triangles, I'm going to get rid of one of these. I'm going to get rid of this. And we look at these 2 triangles. There we go. A is more than the height. But A is something else that's important here. Jack, do you know? It's less than 42. Because if it's more than 42, then it's going to swing down and cut the bottom here, creating a triangle. But when it swings down on the other side, it's going to cut over here. And that triangle will not contain the 30-degree angle. That 30-degree angle will be outside of the triangle. And that's number 4. What if it's 46? And I've used a rough scale here. So let me show you what this looks like. And I have to stand pretty much in front of the smartboard to do this. But you can watch on the other screen if you like. If I rotate this, you can see that it connects right there. So we would get a triangle there. But if I try, let me just fix this a little bit. Good enough. If I try now to make it connect on the other side, so we no longer have this side, and I continue to rotate this, it's going to connect back here. And you might argue that we still get a triangle. You might say, well, here's your triangle. And yes, B is 42, A is 46. But angle A is not 30 degrees, is it? It's some other angle here. We might as well, like I said, I'm trying to attack this from many fronts. How many degrees would this angle A be? Well, 150. It would be the supplement. Is that right? Supplementary angles add up to 180? Yes. It would be the supplement of 30 degrees. because the 30 degrees and that angle have to add to give 180. So in this question, if A is more than B, you get one oblique triangle. We can have two oblique triangles. We can have no triangles, or you can get one triangle that's a right angle triangle or one triangle that's an oblique triangle. And this is one of these topics in high school math that I always describe as being, when you listen to it explained to you, it makes sense. You follow along, you nod in your head, you're going, yeah, I get this. And then you go to put it into practice and your brain screeches to a halt and says, what am I doing? So if that happens to you, that's normal. All right, that is all warm-up. Well, number 5 is still warm-up. So now let's reverse this and let's talk about the 4 cases in general. What is true for each of the following cases? Let's start off with, we can't answer this question yet because you don't know what the case is. Let's start off with 2 different triangles. What must be true if you get 2 different triangles? Well, side A has to be smaller than side B. It can't be, by the way, if side A is ever equal to side B, well, we'll deal with that in a second. Side A has to be smaller than side B, but it has to be greater than the height of the triangle. So it has to be something, and you don't need to draw this. This is me just explaining. It has to be something like this length so that if I swing it down, it connects here for a triangle. If I continue swinging it, it connects here for another triangle, but it can't be so long that it connects here and then it connects way past point A. So it has to be somewhere between. And my computer just locked up. Maybe not. It has to be somewhere between those 2 heights. It has to be bigger than H, which is yellow, and smaller than B, which is blue. Now, the thing about H is if you start talking about sine of angle A being opposite over hypotenuse, you can write that relationship. But that means that H is B sine A. That means that A has to be between B sine A and B. B sine A is just another way of saying the height. So that's case 1. Case 2, it doesn't matter the order I label these in. Let's go case 2 is one right triangle. This is probably the simplest one to describe. If that's the case, A must be equal to the height. Or, since the height is B sine theta, A has to equal to B sine theta, or B sine A. Third case, no triangles. By the way, I should maybe go back here. If I take a look at case 2 where you have one right triangle, the reason why that you get a one right triangle is because H and A are exactly the same number. So when A comes swinging down, it matches H perfectly. Over here, if you have 0 triangles, well, what are you going to do? The only way you're going to get 0 triangles is, like Will said, to have a height that's really big compared to A. Or bigger. I guess it doesn't have to be really big. You chose 1. I think you chose 1 because for sure you knew it wouldn't work. Whereas maybe 20 might have. Maybe. So the bottom line here is that A is smaller than the height, or A is smaller than B sine A. And then case 4, this would be one oblique triangle. I think most people would agree with what somebody had said, that A has to be bigger than B. Does that make sense? Visually, if A is bigger than B, then you're going to get a triangle here, but if you swing this around to the other side, you don't get a triangle that includes that angle A. But technically, saying A has to be bigger than B is not correct. I can make one little change to what I've written here to make it correct. Does anybody know? Do you know, Joel? Right. Greater than or equal to B. Because if A is equal to B, then you're going to get a triangle with A on the right, but when you swing A around to the other side, it's going to just lock up on B and you won't get a triangle. You won't get any triangle at all. So A has to be bigger than or equal to B for that to happen. And so far what we've done here, this is all just a warm-up about you recognizing the different cases that fall under the ambiguous case. And you know what? In reality, the only one that's truly ambiguous is this one. I mean, I said ambiguity means that you can do it 2 different ways. This is the only one you can do 2 different ways. All the other ones are not ambiguous. You either have none or 1 or 2. It only becomes ambiguous if you have 2. So now we're going to take a look at some examples. In this particular question, number 1, you have angle A is 39 degrees. So let me sketch this for you. This is 39 degrees. We have side A, which is across from it, and side A is 14. I guess I can draw that a little longer. Side A is 14. Side B is 10. Well, I guess I should draw it a little bit better, because 14 is bigger than 10. So this is the situation we're looking at. Are you with me on the setup? Angle A, side A, side B. I think it's pretty clear here we're going to get at least one triangle, right? But let me just give you the general idea first. Since this is the setup, this picture we're looking at is the setup, you have to find out which of those 4 cases we're dealing with. Well, A is definitely bigger than B, isn't it? Would you agree? So that means this is a case where you're only going to have one triangle. As soon as you know A is bigger than B, you will know you only have one triangle. If you knew A was not bigger than B, then you have to start looking at the height and comparing A to the height. So since A is bigger than B, you only have one triangle. And we're going to come back to that idea in a second. Let's solve this triangle now. And here's where things will get interesting. All of this moving around of the sides was me in teacher mode. Ultimately, that's why you have an eraser. We've got this diagram now. Okay? So we want to solve this triangle. I know A and angle A and side A, so that's a pair, which means I can use the sine law. A over sine A equals B over sine B. This will allow me to find this angle. And if you like, we can flip that over. Sorry, the past couple of days have been a whirlwind of things in my life, but did I show you that yesterday, that you can flip the whole thing over? Okay, so let's just write it upside down. Let's write sine of 39 over 14 equals sine of angle B, this is angle B, over 10. And nobody had any questions from yesterday's assignment, so this should be like stealing candy from a baby to get B. I'll show my work though. Sine of B is going to be equal to 10 sine 39 degrees over 14. What I need to do is calculate that and then take the inverse sine. All right, 10 sine 39 degrees, close brackets on the 39 degrees, divided by 14, inverse sine of the answer, 26.7. Yes? Good. So 26.7 is angle B. I'm going to put my answers in green. We can find angle C now quite easily by taking those two measures away from 180. 124.3. Sorry? 114.3. There's that extra 10 degrees that I always seem to hang on to. 114.3. Okay. So this is 114.3. We only have one more thing to find, and that's side C. But we can use the sine law again. Doesn't really matter which other sides we use. I'm going to go with sine of 39. Well, I'm going to go with 14 over sine of 39 equals C over sine of C, which we just found to be 114.3. So I'm just using the sine law again. The real meat of this lesson has nothing to do directly with using the sine law. We learned that yesterday. But now we can calculate C. C will be equal to 14 sine, Jack was at 114.3. Thank you. Over sine 39. So this is the actual angle. I'm going to carry all the decimals. I need to take 14 times the sine of that angle, close the brackets and divide by sine of 39, and we're done. The third side is 20.2 in length. Should have been more organized there in my work. Sorry about that. Kind of jumped all over the place. 20.2. 20.2? Perfect.
I think it's 0.3.
Okay. You're right, it would round to 20.3. Any questions with that example? Okay. So let's take a look at the next one. I'm sticking in all of these examples with A's, B's, and C's until you get accustomed to that. Then I can throw out different letters later. So what do we have? We have, well, freehand at this time. This is 49 degrees. Side A is, oh, is this what your question 2 says? Okay, so determine the value of side A that would result in 2 different triangles. So this is 35. To get 2 different triangles, we need a length that is that is larger than the height, so that it will clip that bottom line in 2 places. So we need to find the height. What is the height of this triangle? Well, how many of you just remember it's B sine A? Okay, you can go that route. I'm going to use the trigonometric ratio method and write sine of the 49 degrees is opposite, which is labeled h, over the hypotenuse, which is labeled 35. So h is this number, whatever 35 sine 49 is. $26.4. First of all, do you get the same number? Okay. Why is this not the right answer? Sorry. Why is this not the right answer? Yeah, Myron. No, give me more. It can give me 2 triangles. I'm missing something there. Sorry?
It has to be smaller than 35.
Right. It has to be both bigger than the height, but smaller than side B, which is 35. And how you would write it, and I think this is probably what you wrote, is 26.4 is less than A, which is less than 35. So to get 2 triangles, it has to be in between those numbers. But for the rest of this question, it's pretty simple now because we already know the height. If I say to you there's no triangle possible, then A has to be less than that 26.4. Has to be less than that height. And keep in mind, we've rounded that 26.4. If you wanted, you could write A is less than 35 sine 29 or whatever it was. If you have one right triangle, then A has to exactly be equal to that height. And if you have one triangle that's not a right triangle, then A has to be greater than 35 or equal to 35. I saw that look I got from a couple people. I do need the equal sign there. All right, you guys still doing okay here? All right. You do have a third question though, don't you? Or is that it? That's it. Okay. I just want to point out to you, then we're okay, that if we were to look at question 1, and let's say that I changed question 1. I just want to prepare you for what's going to be expected. Let's say that I changed this to that's a 9, not an A. Let's say I said it was 9 centimeters. Is it pretty clear that there would be 2 triangles? I mean, you'd have to find the height, but I believe the height is going to be less than 9. So if that were the case and there were 2 triangles, then you would need, if I said solve for the missing pieces, you would need to solve both of those triangles. You would have 2 sets of answers. And remember what I told you, when you use the sine law in your calculator to find the angle, it will tell you this angle. not this angle. And specifically, you can set it up on your own, but I'm just going to do it on my calculator. If you use the sine law here, this is a 9. If you use the sine law here to find this angle, which is angle B, I have to write it down just to make sure. It would be sine of 39 over 9 equals sine of B over 10. You would get, for this angle B on the diagram on the left, 44 degrees. Are you with me? Okay. How would you find angle B for the triangle on the right? Because you would still say sine of 39 over 9 equals sine of B over 10. Your calculator doesn't know it looks like this. Your calculator is going to spit out 44 degrees. Myron? You have to speak up, please.
It's going to be, you take the number you got there, minus 180.
Right. 180 minus this number you got for the case of the angle less than 180 or less than 90 is going to give you the angle that's more than 90. Those two angles have to add up to give 180. So you might encounter that. Anyway, I feel a little off kilter this afternoon. I don't know why. I hope that went okay. Some questions to practice in your textbook are continuing on page 108. I suspect that's actually page 109. Maybe it's bleeding on to question 1, page 109. Questions 6 through 12 are dealing with the sine law in general, which can include the ambiguous case. Give me a minute to do a couple of things at my computer, attendance and such, and then I'll be around to help you out.